All right, so we spent the beginning part of the week learning about what kinds of things affect the rate of a reaction, and then you guys did a reaction rate POGL that helped you figure out how to actually calculate reaction rates. So today are just some summary notes for that. This set of notes is in Schoology as always. When you're done, you'll need to add summary and questions. All right, so reaction rates. Rates of reactions can be determined by monitoring the change in concentration of either reactants or products as a function of time. So as we see things change, we can then go ahead and compare how long does it take for those changes to happen, and that helps us develop a reaction rate. All right, so in the reaction, as an example, reaction up here, we have butyl chloride, and butyl chloride reacts with water to turn into butanol and hydrochloric acid. And so what they're going to do here is they're going to record or monitor the concentration of this over time. So at the beginning, it had a concentration of 0.1 molar, and then they give you some data here over time of how that concentration changes. All right. So then, if you go ahead and you look at the average rate over each interval from 0 to 50 seconds, 50 to 100, 100 to 150, 200 to 300, etc. That average rate over each interval is the change in concentration divided by the change in time. Okay, so in this particular case, for this first interval here, we would subtract those two, divide them by 50 seconds, and we would get an average rate of 1.9 times 10 to the negative fourth molar per second. Okay, so again, average rate is the change in the concentration of the chemical over the change in time. So you will notice, if you look at these numbers, that as the reaction proceeds, the average rate of the reaction decreases. Okay, and that's because if you think about it, in order for these two things to react, they have to run into each other. And if there's less and less and less of this, the chances of it running into a water molecule get lower and lower and lower and lower, and so that means that there are fewer collisions between the reactant molecules. So if we then went ahead and plotted that out, time versus concentration of our target chemical, we get a curve that looks like this one over here. And what you'll find is that at any particular point along the curve, we can take the instantaneous rate at that particular moment, and that instantaneous rate will get lower and lower and lower. So the slope of a line tangent on the curve at any point is the instantaneous rate at that time. So for that for the reason that we described before, all reactions are going to slow down over time. So we'll see this slope get shallower and shallower and shallower and shallower. So therefore, if we're thinking about rates and how to report the rate of reaction, the best indicator or the best way to do that is to go ahead and record the rate at the very beginning of the reaction, which we call the initial rate. And that initial rate will become important to us, especially in the next few days as we start talking about rate laws. Right? How do we relate rate laws to stoichiometry? Well, we were measuring the rate at which the C4CH9Cl disappeared. We can also monitor the rate at which another chemical, like the butanol over here, appears. Okay, and that is related to the stoichiometry. You'll notice that the stoichiometry here is a one-to-one relationship between those two chemicals. So therefore, the rate of disappearance of this chemical will equal the rate of appearance of the other chemical. Okay, so in other words, they are equal but opposite in sign. So that was nice. What happens if the ratio is not 1-to-1? Well, here's another reaction that we have. Right? And in this case, if we're going to compare the reaction rates between the HI and the I2, okay, we will see that for every two of these that disappear, one of those appear. So as a result of that, you're going to get this is going to disappear twice as fast as this appears, or in other words, this is going to appear half as fast as that disappears. So the reaction is going to be -1/2 the disappearance equals the appearance, okay? Or double the appearance equals the disappearance. If we generalize that idea then for any reaction that has these species and the lower level coefficients, the rate is always going to be 1 over the coefficient of the species is equal to 1 over the coefficient of any of the other species as we roll along. All right. Great. So that's how things are related, and that's a little bit about how we measure reaction rates mathematically.